Hey everyone, how's it going? This is Aaron speaking, and welcome to my presentation for the final project for this course on Monte Carlo kernel density estimation. And I'm going to be presenting it with an application, or really a motivating application, to electro-optical image sensors. So, I'm still trying to figure this out. Hold on. Alright. So I want to start this thing off with a really simple question here. We got two images, and the question is which one is better in terms of its image quality. Now I don't think it takes much discernment here, but we can see that the right hand side image shows poor image quality. It's very noisy. And so what the point of this is that I'm trying to demonstrate the effect that something called read noise has on an image. And for anybody who has any electronics background, read noise can be thought of as the noise floor of the camera. So there's always some bit of noise present in the image, and this becomes very prominent in the image when you're trying to take an image of a scene under low light conditions, right? So as the light level, or as the illumination level gets low, this read noise starts to dominate, and we see a very noisy result in our final image. And so the reason why we care is we want to be able to, given multiple cameras, we want to know which one is going to produce the best image under a given lighting situation. And the question is how do we quantify that quality, or that performance metric of a camera? So what I'm going to do is step through three, this thing is going to be broken up into three major sections. We're going to go through and look at, just provide some preliminary information about the photon transfer method and how it's used for characterizing the performance of sensors. I'm going to present the theory aspect with the analysis that goes along with it, and then I'll show some examples, some numerical examples in MATLAB of applying these various theoretical aspects. So we'll start off with the preliminary information just to motivate this thing. So we saw in the previous couple slides ago, we saw the effect that read noise has on an image. We want lower read noise in most circumstances. So to quantify that, we use a technique called photon transfer. And where this thing gets its name from is that image sensors, and I'm talking about digital image sensors here, what they do, how they work, is they take photons of light from a scene. Those photons are going to interact with the sensor, and that sensor converts or transfers those photons into packets of charge, or packets of electrons. And these electrons make their way through the circuitry of the image sensor and are eventually digitized and converted into digital numbers. A lot of people know them as gray values. And so the photon transfer method, what it does is it seeks to measure various performance aspects of an image sensor and quantify them in an absolute sense. So we saw read noise, but there's many of these things that photon transfer can measure. And the measurements are absolute. And what I mean by that is the final measurements that come out of this photon transfer method are always in electron units. And the reason why that's important is because the electron is a physical quantity as opposed to a gray value, which is arbitrary. So if we attempted to characterize the sensor in terms of gray values, we could not actually compare to the numbers, if you will, from two different cameras or sensors, because they would not actually carry any meaning. So we need to be able to make our final measurements in absolute units of electrons. And the way we do this is we measure something called the sensor conversion gain. And what this thing is, it's a constant. And it's a constant to allow us to convert measurements in digital numbers, as dn, back into units of electrons. And the photon transfer method requires multiplying all of our measurements by this conversion gain constant. So it's really important that we measure this thing accurately. The reason why is the uncertainty, and if there's any bias present in this measurement, this conversion gain measurement, fundamentally limits the uncertainty of the method as a whole. So for example, we see at the last line here, this read noise. The way we get it is we measure the read noise from the sensor in digital numbers and gray values, and we multiply it by the gain. And this is the same sort of process for all these other measurements. We have to multiply it by the gain. And so what we end up with is, if there's a lot of uncertainty in the gain, there's a lot of uncertainty in all of our measurements, and we really want to be able to control that. And so this is where I've spent the last several years of my life really working on modeling the distribution of this gain and looking at how do we control its uncertainty. And so this leads us into how we actually measure this thing, just to provide some more of the statistical model behind it. I want you to consider an image sensor that's made up of an array of pixels, and I want you to just think about one pixel. We're measuring the gain of just a single pixel. And the way we do this is we take two samples, right? We can think of every time we observe that pixel, we are observing a random variable. And so we will set the camera in the dark and we'll observe that pixel a bunch of times, and we'll get this bold font Y here. I think I can draw here. Yeah. Bold font Y here is a sample of observations of the pixel in the dark. X is going to be the illuminated sample, so we'll shine a light on the sensor, and we'll do the same thing. We'll observe the pixel a bunch of times. And so what I did was I modeled these two processes as being normal, which actually turns out to be a quite useful model. It works quite well. It makes a lot of the computations much more tractable. So the way we get this conversion gain measurement, which I'm going to call capital G to denote that it's a random variable, is we take the sample mean, the sample variance of each of these two independent samples, X and Y. The difference of the sample means we see in the numerator of G, and the difference of the variances we see in the denominator. And I know that's not the hat there is not a typical notation, but that's what that means. So we have the difference of the means divided by the difference of the variances, and by using this normal model we can conclude that the difference of the means is also normal. Here it is. The difference of the variances is this gamma difference distribution. So each individual variance is a gamma distribution, or it's distributed according to the gamma, and so the difference is this so-called gamma difference distribution. And so the goal is to be able to study the properties of this conversion gain estimator under this model. And so with that, a couple years ago, I worked on deriving this thing which I called the centralized inverse-Fano distribution. And so the way it's defined is that if we're given two independent random variables, x, which is normal, y, which is this gamma difference distribution, and we define g to be their ratio, then we say that g has a centralized inverse-Fano distribution with a million different parameters. And so the first thing that I had worked on was deriving the density and distribution of this thing. Unfortunately, it's so complicated that I was only able to find a solution for these things when these alpha 1, alpha 2 parameters, or shape parameters, are integers. And this happens to still be useful because these shape parameters represent sample sizes, or they're proportional to the sample sizes. And so in many cases they are integers, which is nice. The problem that persisted though was that these solutions are absolutely hideous to look at. They're very long, and they're very hard to compute, even with a closed form solution, particularly around the origin. There's a lot of issues with evaluating this density and distribution around the origin. And so in these sorts of cases where you don't have an explicit expression, a lot of times we can turn to evaluating the density, distribution function, etc., with numerical integration. However, even this is problematic with the centralized inverse-Fano distribution, and because of the special functions involved, it starts to numerically fall apart for large parameters, shape parameters. And what makes this even more complicated is that this random variable g does not even have any well-defined moments. So another example to kind of put this, make this a little bit more real, is the Cauchy distribution. We know that the Cauchy distribution has no well-defined moments. If you try to evaluate its mean, you will find that it is undefined. And so mathematicians are pretty clever in coming up with extending the ways we can find quantities. And so one way around this problem is to use something called the principal valued expectation. And the way we can see how it's defined here for the centralized inverse-Fano distribution, this principal valued expectation is defined as the following limit, where we integrate. You can see the integrand here looks like the integrand you would use for finding a mean, but we're only going to integrate it over an interval centered on the origin, and then we're going to take the limit as the interval endpoints tend to infinity. What this does is it gets rid of infinities in the final solution. So in the case of the Cauchy distribution, right, here's our Cauchy distribution, and we know it has a median, let's call it gamma, which can be non-zero. It's a location parameter. So what this principal valued expectation would find if we applied this to Cauchy distribution is that this PVE value here would be in fact gamma. So it does give us an actual center of the distribution that behaves in many ways that a mean would. Now I was able to find an explicit form for this for general shape parameters, which was wonderful. But the problem that I ran into before is that for large shape parameters, this thing too becomes difficult to compute, and that has a lot to do with the very, I would say, exotic special functions that are required to evaluate it. And so we kind of have this problem of how do we actually even compute these things. So here's the problem. We have this gain. We wish to study its properties. We have its density distribution and even its mean, which is useful for talking about things like its bias, but they're all really hard to compute, and so that doesn't make it very useful. And so what we want to do is come up with, we want to solve two problems. We want to be able to evaluate the PDF, CDF, quantile functions, etc., these probability functions, and do it quickly. But we also want to estimate this principal valued expectation. And so what we're going to do is try to solve this with computational statistical methods, and in particular the Monte Carlo approach. We're going to actually use Monte Carlo to solve both of these problems. Okay, so that's enough of the preliminaries. This brings us into the supporting theory and analysis. So there's going to be two main theorems that I'm going to present. The first one has to do with estimating the probability functions. So theorem one here, we're going to apply the Monte Carlo approach and recast the CDF, the distribution function of G as an expected value. And so here's the theorem. If G is centralized inverse-Fano distributed, then its CDF can be presented as the following expected value, where this capital phi here is the standard normal density function. And you can see where it's a function of G, and we're taking the expected value with respect to Y, which is a gamma difference random variable. And so here's the proof. It's actually it looks like a lot, but it's quite straightforward. We have G up here. It's a ratio of independent random variables x and y. So if we write out the distribution function, the probability of G less than G, well, by definition, that's the probability that x over y is less than G. And if we try to solve this inequality for x, we have to consider the possibilities that y is negative and y is positive, and this leads to the two terms here. Y is positive there, y is negative here, and these two probabilities represent two 2D regions in the xy plane. And so for the first one, we have y greater than 0. Well, there's the y greater than 0 piece, and then there's the y less than 0 piece. And if you just sort of work through the math, the joint density of x and y, since they're independent, is the product of their densities. We can solve the first integral symbolically because it's just going to be in terms of the CDF of x. And we plug in the CDF of x here, and working with its definition, you can end up writing this thing as a single integral. And you can now see there's an expected value here with respect to the density of y, and so we have our solution. What's nice about this particular example is that we can get, once we have this initial expected value, we can actually get the density and higher order derivatives essentially for free, because we can differentiate the expected value under the integral sign. So we present the following corollary for centralized inverse-Fano distribution. We get its density and the derivative of its density here as these following expected values. Little phi is going to be our standard normal density. And the question that you may be asking is, why do we care about the derivative of the density? Well, what we're going to do in the application is we're going to invert this Monte Carlo estimate of the CDF using a technique that requires the density or the density and the derivative of the density of G. So that's why these things are being presented. Okay, so we got these Monte Carlo kernel density estimators, as I'm calling them, for this SIF probability functions. And I think it's important to point out here that this term, Monte Carlo kernel density estimator, is not a standard term. I could not really find a lot of information on an actual method, if you will, a name for this thing. And so I've just kind of called it this, and I guess you'll see why I call it by this term. But anyways, here's our three estimators for the distribution, density, and derivative of the density. And we're just applying the Monte Carlo method to those expected values we just saw. Each of them requires some sample of gamma difference random variables, which is very easy to do. We'll see that in a minute. And we get these three different estimators. So when I first did this, again, I couldn't find a whole lot of information on this. The first thing that I was worried about was whether or not this was really a legitimate thing to do at all. And are these even valid probability functions in their own right? And the actual answer is they are. And I provide here an example. If we go back to the estimator for the density here, if we do a little bit of algebra, we can write it as this right here. And what we see, this phi now as being the general normal density, so for just any mean, any sigma, that's how we write it. And what we see is that this estimate for the density of G is actually a normal mixture distribution with n components, and the mixing component here is the same for all of them. It's 1 over n. And so what we see is that we're adding up a bunch of normals, and it being a Gaussian mixture, we know that it's a valid density, and therefore it must be that the estimate for the CDF is also a valid CDF, because we can just integrate the density, right? So we get this Gaussian mixture, and this might look to you like an example of a kernel density estimator. So we have this normal kernel here, but we also see that it's got this weird sort of look to it. It's got this, it doesn't have a constant bandwidth, and the bandwidth is actually a function of the observations of the random variable y. And so this is an example in the book. I looked this up. There's something called adaptive kernel estimators, where the bandwidth changes depending on the observations we make. And the book actually talks about how nonlinear transformations of random variables, you can represent them as these adaptive kernel density estimators. And that's basically what's going on here. This is where I got the name. It looks like a kernel density estimator. It behaves like one, except in this case, we have an exact form. We're not trying to guess at a bandwidth that works. We know the exact bandwidth. And so another quick question I asked was, does this thing even have similar properties to that of the centralized inverse-Fano distribution, or the SIF? And so I looked at, well, I know that the SIF doesn't have a mean. Does this thing have a mean? And so here we're taking the expected value, and keep in mind, this is with respect to G now, not Y. So we take the mean, right, here it is, and we get the following result. And you say, it does have a mean. The SIF does not. It's not an accurate portrayal of this distribution. Well, sort of. It doesn't really have a mean in the sense you might think it does. So what happens is there's this thing called there's a generalization of the central limit theorem that goes beyond a normal limiting distribution. And it turns out that according to this generalized CLT, as we take n to infinity, this piece right here, which you'll notice is the same as this, it doesn't converge to a constant as you would expect a normal sample, a typical sample mean to do. It's not a consistent estimator, and so it actually converges to a Cauchy random variable. It never settles down, and it fails to converge. And this does, in fact, agree with the properties of the SIF. So we're getting green lights here. So some further considerations about the various aspects of this estimator, be its bias and variance, are important. Now we know by definition that all of those derived estimators are in fact pointwise unbiased by their very definition. So we have in particular for this the CDF here that its expected value is going to be equal to the exact distribution for the entire domain of G, the entire support, which is good. Now finding the variance actually turns out to be a very difficult task, because we end up with the square of the normal CDF inside an integral, which is just not tractable, at least in the form I have it. But to get, we can actually find an approximation. And so in the context of the conversion gain measurement that I've been talking about, it turns out that in nearly every case, the variance of this gamma difference variable completely dominates, or nearly dominates, the variance of x. And so if we consider this, we can think of x as being degenerate, so it has a delta function as its distribution centered at its mean. And it has this delta function distribution with respect to y, because y has much more variance. It almost behaves like x is a constant. So what we can do is if we take the expected value definition of our density, or I'm sorry, not our density, our distribution for G, and we take the limit as sigma goes to 0, what ends up happening is, so like, here's 0. Let's just consider the standard normal distribution. So here's like for a large sigma. As we let sigma go to 0, what we end up with is essentially a step function, the Heaviside function. And so what we really end up with in the limit is something like this right here, where we have an indicator function as our random variable. And what's convenient about this is that now we have essentially a Bernoulli random variable, this indicator function here, because we're either 0 if we're not above the mean, or we're 1 if we are. So the limiting distribution is 0 here, and it's 1 here. And so if we take the sum of a bunch of these, just crossed it right out. Take the sum of a bunch of these things, we end up with a binomial random variable, and now we have a tractable way to get an estimate for the variance, and here it is, right? So here's our estimate for the variance under this approximation. And so if we go on here, just some facts this tells us is if we look at this estimated variance, this approximate variance, and we take G to plus or minus infinity, we get 0. So we know the variance approaches 0 in the limit. And we also know is if we evaluate the derivative of this estimate, right, and we basically perform our second derivative test, so we set the first derivative equal to 0 and solve, and we get the solution must be when the distribution is 1/2, which happens to correspond to G as being the median, and we can take the second derivative and show that it is less than 0. So we know that the median point here is a maximum. And when we actually solve this thing, what we get is this solution right here, which is remarkably simple. And we find that approximately the maximum variance of this thing is 1/4n, which again is going to occur near the median. And so the variance is certainly not constant. And let's show an example of this. So here I'm using just n equals 1, because so sample size of 1. And what we're seeing here is this is not a density function. This is a plot of the variance of our CDF estimator is a function of G. And you can, in fact, the blue line is the analytic, our approximation here. And then, the scatter plot points here are estimates of the actual variance using a simulation. I provided the code for that in the appendix. The point is, though, is that you can see that it actually does a pretty good job for the parameters I used. Again, these parameters are very realistic for the types of these conversion gain measurements. So we have a pretty good estimate for the variance. It does seem a little low. It's a little low in certain places, but nonetheless, I was quite pleased with it. Okay, so that's the first part. Second part here is the second theorem for the analysis section, and we're looking at finding a principal value, an estimator, if you will, for the principal valued expectation of G. And so, as I pointed out before, I have found an exact expression for this thing. It's an explicit expression that is nice in theory, but again, for large alpha 1, alpha 2, it gets hard to compute. And so we ask ourselves, well, in the case where we have large shape parameters, how do we estimate this thing? The first thing that I would point out here is that the principal value mean of G can be broken up into two components. Very much like an expected value of any ratio of independent variables, you know, y, or try x over y. If they're independent and the expectation exists, you can pull apart. So when we do this for the principal valued expectation of G, we get two pieces, mu, and this PVE y inverse. And so I mean, mu is quite easy to compute. It's just a constant. So the question really is, how do we estimate this principal value mean of y inverse under large shape parameters? And we'll again call on the central limit theorem and note that as these shape parameters get large, y, this gamma difference random variable, is going to converge in distribution to a normal distribution, normal random variable with its equal mean and variance. And so under that, we're going to basically from here on out assume that this gamma difference distribution, that the shape parameters are large enough such that we can call it normal. And so now I present the following theorem for finding, or essentially writing this thing as an expected value problem. And the theorem reads that if we have y being distributed as normal, and we have a uniform random variable u over the interval 0 pi, then for some constant delta greater than 0, we have this principal valued expectation of y inverse being defined in the following manner. And this thing looks very strange. First thing to notice is that we have this term. It's an expected value with respect to y, this normal random variable. The second term here, we see the density of y appearing, and we also see that we're taking an expected value with respect to this uniform random variable. And even more strange is we have complex numbers appearing. There's the complex number I there, and there. And so this is definitely not an intuitive result. And actually something that it was a lot of fun deriving this thing, and I'll give you the gist of how it works. For any of you who have taken complex analysis, you'll know, you'll get this, but I assure you can follow the basic principles here of what's going on. So here we go. Principal valued expectation of y inverse. The first line here is the definition of this thing. So we're taking the expected value 1 over y. It doesn't exist, so we find it in terms of this Cauchy principal value, which ends up being that we're taking a limit. And so this first integral here, we basically have an interval. So if here's switch over to black. So here's our number line. This is y, right? Here's the origin, and we're basically saying is we're going to integrate. Here's epsilon minus epsilon. We're basically going to integrate all of this stuff here and here off to infinity, and we're going to take that limit as epsilon approaches 0. Well, what we're going to do is we're going to split this up into two pieces. We're actually going to define another constant called delta. So here's minus delta, and here's positive delta. And we're going to just take the integral over this region greater than delta separately. So we'll take that integral, that's our first term, and the second term is going to be this piece plus this piece, which doesn't really seem like it gets us very far. But what we can first do now is write our interval over y greater than delta as this expected value, which is defined in its normal way. And now we have this second piece here. And what we need to do is to be able to write this integral limit combo as an expected value. So we use complex analysis and the Cauchy residue theorem to do that. So what we're going to do is we're going to define, it's called the contour integral, which is nothing but an integral where the path of integration goes into the complex plane. And we're going to define this thing to be j. We're integrating f of y of z over z over this contour c, which I've shown below, and c is a closed contour. So here is our real number line right here, and we're going to integrate c, which is 4 pieces. So we got gamma 1, gamma 2, gamma 3, and gamma 4, and you'll notice the thing is closed. And you'll probably be wondering, why is this useful at all? This seems like we're making the problem much more complicated. And the reason why is that if our density y here has some nice properties, then we know by, go to the next slide, the Cauchy residue theorem, that the entire integral over c is 0, which happens to be the case of a normal distribution. This works out to be true. And so we have this integral over each piece, these 4 pieces, integrates to 0. We just kind of write this thing out, and then we do our parameterization. So like, for example, here, that's that little arch over the origin. We define z equals epsilon e to the I phi, and then dz is going to be I epsilon e to the I phi d phi. So we're just parameterizing over that path. And so we solve for these 2 terms right here, and if we take the limit as epsilon goes to 0, so now we're taking the limit as epsilon goes to 0, we have a solution for our integral. We got 2 pieces here. The first piece turns out just to be a constant, and then the second piece, what we've done here is we have an integral over a finite interval, and we divide and multiply by pi to turn this into an expected value problem with respect to a uniform random variable. So we're kind of Monte Carlo integrating this entire thing twice. We get, here's our final solution. We have the first piece, which we derived earlier with respect to y. This second piece, that's with respect to u. This gives us the PVE y inverse in terms of an expected value problem. So we now have our asymptotic estimator for PVE of y inverse, which is this nasty looking thing right here. Couple important points is that we need 2 random samples. One's a gamma difference, y, and one is a uniform, u. Some weird things is that this thing is a complex valued random variable, and the parameter delta, while arbitrary, how do I say, not all choices are equally as good. And we'll see that in just a couple slides. So what do we pick for delta is a little complicated. We'll show in a second. We know that our estimator is unbiased when y is normal, and I guess it's asymptotically unbiased for the gamma difference distribution. And to find its variance, I thought this was really cool. We're using some of the stuff we got to learn this semester. To find the variance, we actually used the definition of the variance as an inner product for this complex case to get essentially the variance right there. And this is for an arbitrary random variable z. We'll see if we apply this, we get this huge ugly mess. There's not really much important things to point out here other than we have an explicit expression for the variance. And to see what happens as a function of delta, I provide a simple example. So here's the plot of the variance of this estimator as a function of delta, and I just picked the simplest parameters I could come up with, lots of ones. And what we see is that when we change the value delta, the variance changes, and we actually get a minimum value somewhere around here, maybe a little bit less than 1. And so pick the value of delta. It is arbitrary, but it does require some sophistication. We need to find a good value. That's something I have not done. That would be a lot more work than what I've already done. But the idea here is that it does matter. And then, so one more thing is the expected value with respect to u can be evaluated as a power series and you can see the solution I got for doing that. We have a power series in terms of these Hermite polynomials. It was, again, is another thing we got to learn this semester, so I thought that was really really cool. Because it is a power series, the idea is that we can just take the first few terms and use that as an approximation to the expected value that we had with respect to u. There it is. And we'll see how that works. Basically, we're trading off, we get rid of the variance of the estimator of estimating those uniform random variables, and we basically trade it off for a little bit of bias because we're just taking the first few terms. Okay, so that was, you're probably sleeping by now. And so here's the last section of this talk, which is just going to present some quick numerical examples just to show these ideas work. So the first application was finding the quantile function for the SIF distribution. So we have a good estimator for the distribution function, this hat fg, and I say it's good because we know 1, it's unbiased, 2, it is a valid CDF, 3, it's an infinitely differentiable and continuous function in G, and since we have its derivatives, we can use root finding algorithms that are based on derivatives. So we'll invert this thing by basically solving this. We'll pick a value at u, that's our quantile, and we'll solve this equation for G to get the inverse CDF, the quantile function. And we did a lot of root finding algorithms this semester. So here I decided to go, we learned Newton's method. Here I decided to go with Halley's method, which is a third order algorithm. And we see the updating equation here. Again, it's based on the CDF, the density, and the derivative of the density. All of these things matter. And again, for down here, it's not really important to go into the y, but here is a good reliable starting point for 2 different cases. So MATLAB code, again, here's our updating equation. This is a very sort of rudimentary algorithm. We're just going to provide a guess and keep updating the guess until we're within some sort of relative convergence criteria, and it ends. There's not really a whole lot to explain there. So here's the inversion routine for finding the quantile function. We got just some example parameters. We got our starting point. Here is our sample of gamma difference random variables, and we just take a large sample. I took a sample of 100,000, and here's our 3 different Monte Carlo estimators, or estimates I should say. You'll notice that each one is just based on a mean. This is the mean of some function. We plug all of these things into this Halley's method, and we can evaluate the inverse CDF or quantile function for G. And here is what I got using the parameters above. We got our derivative of our density. Here's the density of G, which is very strange looking. It's this bimodal, sort of heavy tail, wild looking thing here. Here is our estimator for the CDF, and finally the estimate for the inverse CDF. And you'll notice these things are actually quite smooth, and they're actually differentiable. This has to do with the differentiability of these estimators, why they look so smooth. I was going to plot the exact functions on top of these so you could see, but they were so close to each other that it was really indistinguishable. And that's what I point out here. Indistinguishable from the real thing, at least visually. This is not, visually indistinguishable. Output is smooth and continuous. I ran this thing 5 times and estimated the 2.5% and 97.5% quantiles, and to run the entire thing and to get those quantile values took about less than a fifth of a second. So it was extremely fast. The one caution to point out here with the inverse CDF is that even though the variance of this estimate dies off to 0 at the limits, very small errors in the extreme tails in the CDF result in much larger errors in the quantile function. So this thing's really not going to be super great out in the extreme tails of the distribution. It can actually be in quite a bit of error. So that's just one limitation to point out. So here's the second application we're estimating this principal value expectation of G. Again, so we got some parameters. I used a delta value of 1, and I'll skip down to the end first. There's the exact value using this PVY inverse function, which I provide all three. These three functions are all in the appendix. So this is the exact one, and this is, let's see here, this is the estimate using a sample of Y, a gamma difference distribution, U uniform. Here is our series approximation, and I just used the first three terms, so the 0, 1, and 2 index terms. If we go to the results, that is totally not the right results. It turns out this is the wrong slide. It turns out that they were very close to each other. When I evaluated a bunch of these things, I got that they agreed in mean and showed different variances. So just wrapping up some general comments. This technique that was employed is very easy to do, and this is very convenient when we're dealing with functions of many random variables. The densities and distributions can be very hard to find, but if we can write it as an expected value, we can sample these things. It's very easy to do this. And this works for arbitrary and very complicated functions. In many cases, but not always, we have some flexibility. The result we get, the estimator we get, can be written so that it's differentiable, which allows us to use root finding methods like I discussed. And one thing I did consider here was this could be compatible with importance sampling. So if we wanted to reduce the variance of the estimate at certain points of interest, I thought about this, and I certainly don't see why you couldn't do this, although it may not be very easy to do. I'd have to think about that more. But those are the pros. Some of the cons is that one, you're performing very large samples. The precision in the extreme tails is problematic, and also we still have to evaluate. Like for this example, we had to evaluate the normal CDF a lot, and especially out in the tails of that thing, there's questions of numerical stability, perhaps, or really just precision concerns. So there are certainly drawbacks to this thing. There's just I won't go through these, but I provided this is the code used for the variance way back towards the beginning here, looking at the variance as a function of G. I provided a proof of the series expansion version of the PVY inverse estimator. You're more than welcome to look at that if you like. And then there's the last three is just these MATLAB functions that were written to estimate the inverse of this PVE value and sources. So that concludes this presentation. I thank you very much for listening, and really enjoyed working with all of you this semester. Wish you the best of luck.